This is Charles Sanderson doing another Aspen Custom Modeler ACM demonstration video. Thanks to everyone who's left likes and positive comments on the website. I really appreciate that. It does encourage me to do more. What I thought I'd do today is run through another sort of tips and tricks video. One of the things I've run into many times is trying to get correlations to get coded into ACM, and then once coded, get them to actually converge reliably. And so there's a few tricks that I've learned along the way that I've got to share. For the purposes of that, I'm going to have a quick look at the Darcy-Weisbach equation. I'm pulling the engineering toolbox. If you haven't come across it, it's a great collection of data, correlations, equations, all sorts of useful stuff out there. For the pressure drop related to the flow, then I've got this equation. This in itself isn't a terrible equation. I've got to divide by diameter, but that's not a big problem. I'm usually going to be fixing the diameter, and it's usually going to be a non-zero value, so that should work okay. But I've got this friction factor in there, and I'm going to try and calculate the Colebrook equation. And that Colebrook equation is one of these sort of typical engineering correlations that's a bit of a mess with all sorts of challenging terms. I'm dividing by things, I'm taking square roots, I've got logs of things, so there's lots of potential for the maths to get messed up if I get negative values or zero values feeding into some of those systems. So what I want to do is take this equation and work out how I can reformulate it to work well in ACM. So what I'm going to do is drop it into Word just so you can see what I was thinking. I'll take this value that I'm taking the log of, I'll make an intermediate variable in f-inter based on that, and then I'll multiply through those multiply through those fractions, and then I'll multiply the whole thing through so that I have nothing is being divided by anything else. So I'm avoiding the chance of a divide by zero error, and taking advantage of the fact that ACM can have multiple variables on the left-hand side of an equation as well as on the right-hand side. If I were thorough, I probably would divide through by 3.72, but that would put a divider over here, so no real advantage. And then finally, this f-inter, I'll put back into this equation, multiply through by the square root of f, and again avoid that divide by zero potential. And I've now got two equations in the place of one, but I've got rid of all the divide bys and hopefully have a more reliable solution path. Coming into ACM then, what I've done in ACM is I set myself up with a very simple environment. My port that I've defined is got just pressure and flow. I'm forgetting about composition, temperature, enthalpy for now, just for purposes of this demonstration. And my stream is a very simple in equals out calculation, but the one thing I've done is to make the model square. I'm taking advantage of the structure of the system so that if the inlet is not connected, then I fix the flow and pressure by default. That just makes my whole model square. Talk about that a little bit more in video 13 if you're interested. Okay, finally then my pipe, I come in and I'm going to define various things that I'm going to fix. I've got my length, diameter, and roughness. I'm going to, in this case, choose to fix my viscosity and density. Normally I would calculate those using physical properties call, but since I'm not tracking temperature or composition, I'm just going to fix those for now for demonstration. I then have my intermediate variables being calculated, so my volumetric flow, my Reynolds number, and so on. This f-inter that I calculated, and my ports. So my flow out is equal to my flow in, my pressure out is equal to pressure in plus the pressure drop. My volumetric flow times my density is equal to the mass flow. Again, I could divide through by density, but I avoid divide bys wherever I can. My velocity is then the area times the volumetric flow. Calculate my Reynolds number. Oh, sorry, one thing to notice, and this is one of the things that often trips me up in ACM. Velocity is defined as flow vol, and if you dig through the definition, you'll find that the volumetric flow is defined in terms of kilos an hour. And so my velocity is determined in terms of meters a second, so I've got meters cubed per hour, meters per second, so I've got to multiply through by 3600 the number of seconds in an hour. Similarly, for my Reynolds number, viscosity is defined in terms of centipoise rather than Newton meters squared. Newton meters. Regardless, I need to multiply through by 10 to the minus 3 to get my Reynolds number to work out, and again, avoid divide by 0. Then I've got the two equations that I showed you in the Word document. to calculate f-inter using based on f. And then finally, I've got the Darcy-Weisbach equation of pressure drop. And again, pressure drop is determined in terms of bar, and I want it in terms of Newton per meter squared. And so I need to multiply that by 10 to the 5 to go from bars to Newton per meter squared and get everything else to be in the right units of measurement. Okay, so I've run through quite a lot there, but hopefully that covers what you need. Okay. So now let's actually try and get this thing to work. So I'll drop a pipe onto the flow sheet. I'll call it pipe. As in video 13, I chose to force myself to name the blocks, but I'm letting ACM name the streams. That's a setting or a preference that you can have. Excuse me. Tools, settings, preferences. No, it's not. It's an auto name. So that's what I did there. The other thing that I've done to make it easier to track things down is I've got my solver reporting level set to high, so right click in the simulation messages window to high, and then on the solver options, I've come to my nonlinear solver and I've chosen to show the highest two variable and residuals at each iteration. That's just going to help me see what's going on. The other thing I've done, just because I always do, is I've set my conversion criteria to both residual and variable. Okay. So now let's see, does this work? So let's hit run. And you can see it does, it converges, but it's taken 10 iterations, which is quite a lot. And if I have a look back up at some of this debug information that I've learned, you can see that I'm starting off with a fairly large error. It runs through and it's running into a square root of a negative number. ACM has fixed, actually, sorry, it's the log of a negative number. ACM has, I think, fixed in one of their releases in the years, so that this taking the log or the square root of a negative number doesn't cause ACM to fail to converge. It muddles through, but it does throw a wrench into the works, and so you want to try and avoid that if you can. Nonetheless, it gets through with that negative error. It then comes through and it's pushing the error down at each iteration, 10 to the minus 3, 10 to the minus 2, 10 to the 0. The equations having the most trouble is this ff_int. If I have a quick look at my code, one of the things I like to do is actually label my equations. So I've called my equations various things. So now I can see, rather than the error message saying pipe.equation 300, it's saying it's ff_int that has the large residual. And so I can actually see that this is the equation that's causing its grief. And it's not surprising because there's lots of non-linearity in that equation, so it's going to have a hard time converging it. So what I can do though with this error turned up is I can see that ff_int is causing the biggest problem. The two variables that are being calculated or that are being used in that equation are f and f_inter. And then when the next iteration, it starts off by telling me it's moving the value of f in the pipe from 1.15 down by 0.97 and so on. So you can see how it's moving the variables, which equations are causing grief, which variables are moving significantly. And this is often a good way to then debug and see what's going wrong. It's also warning me when I'm taking square root of negative numbers, square root of logs of negative numbers, and so on. Nonetheless, it muddles through, and eventually, after 10 iterations, it comes up with a solution. So that's good, but it's not as good as it could be. So what could we do to change this? Well, I've got my text for pipe up there. One of the things I've noticed is that I was getting negative numbers in the system. So if f ends up as a negative value, that's going to be a problem. I've defined f as a no type, which means it has a lower bound of minus 10 to the 30. That isn't necessary. F is always going to be positive, I think. Similarly, Reynolds number is always going to be positive for a meaningful solution. So what I can do is I can come through and I can change some of the bounds on these variables and get them help ACM know where it's going. So again, rather than forcing you to go through the pain of watching me type things, here's one I prepared earlier. So what I've done is I've come through and I've made Reynolds a positive rather than a no type. No type's a useful sort of catch-all variable type, but it's got very wide bounds, and so it's challenging Positive has a lower bound of 10 to the minus 9, 10 to the, 10 to the minus 9, and an upper bound of 10 to the 9. So that's a better starting point. In fact, 10 to the 9 might be a little bit lower. I may need to raise its upper value, but for now, I'll assume it's good enough. Square root of f I've also made positive, and f inter I've made positive. I'll come to that in a second. And f I've left as a node type. Since I've made this a positive with a lower bound of 10 to the minus 9, this is a potential 10 to the minus 18. I'm going to set it to a lower bound of 0 just to give it a little bit more wiggle room. No real magic to it. I'm just it's a bit of art as well as a bit of science in here. The other thing I've done down here is I've commented out using the square root. It's there and it solves, but I don't really trust it. So what I've done instead is I've created another intermediate variable, squirt f, and then I've said I could use the p-power function, but instead I'm saying I'm squaring both sides of the equation to say f is equal to square root of f squared. So now I've still got this log 10, which is potentially troubling, but because I've forced f inter to be a non-negative value, the danger of taking the log of 0 or the log of a negative number is averted, so hopefully that will behave well going forward. Okay, so you can see how getting rid of the square root, putting better bounds on things. The other thing I've done is I've come in and I've provided initial estimates to try and get that starting point slightly better. That often helps get the convergence to work the first time as well. Okay, so that's all good. There was one other problem that I had laid for myself, and I always forget about this one. This is one that you may run into as well. You remember I declared pi as a global parameter, and that's great in a model that I've been working on for a while, but since this is a brand new model, and I've never done anything with it prior to this demo, I haven't necessarily given pi a reasonable value. I just declared it as a real parameter. So let me have a quick look at my globals, the all globals table. You can see, yeah, as I feared, pi has a value of 1. What I want to do is set that to a more meaningful value of pi. I need to worry about it the very first time that I use it. After that, it's going to be okay. So there we go. Run. Because I changed the value of pi, I changed the relationship between volumetric flow and velocity. And so that then changes with the velocity changing, that changes the Reynolds number. With the Reynolds number and velocity changing, that then changes all these other equations. So I need a few iterations to resolve my system with a reasonable value of pi. Now that I've set pi correctly, though, the system's going to work just fine, he says confidently. And so now I can test my pipe 2 as well as my pipe 1. To make things slightly more interesting, what I'm going to do is, oops, the wrong button there, is going to find all my variables, and I'm going to, other than the value of pi that I've just gone through and set, I'm going to reset those to their default value to force that whole thing to solve again. Okay, so I've got my different models set up. What I want to do now is compare the convergence of this pipe 2 with the original pipe. So I'm going to call this pipe 2. I'm going to give it a feed stream, and I'm going to hit run. And if I come and have a look at my error messages, you can see pipe 2 has converged in 5 iterations, where pipe 1 took 10 iterations. And if I have a quick look at how pipe 2 is converging, it starts off with a fairly good estimate because I gave it those initial conditions. You can see I'm not hitting any of those taking the log or square root of negative number issues, so that's helping it converge. I am running into a little bit of a challenge, so that ffint is once again a very nonlinear and therefore difficult to converge equation. It's moving the variables around a little bit. That first step that it takes actually puts the system in a place where the error goes up on that ffint equation. So instead of being 10 to the minus 5 times 10 to the minus 10, 5 times 10 to the minus 1, it becomes 4. But I'm then going to trim those numbers back, and it goes from 4 to 0.6, which is still higher, but then it trims it again, and it gets it down to 2 times 10 to the minus 2, and then it converges pretty quickly from there. So this is converging a whole lot better. Is it essential to do this? No. But what you'll find is in large models, reformulating like this can really help the overall system to converge somewhat better. Okay, the last thing I'm going to show is what would happen if I change the system up a little bit. Let's go with another pipe 2. I'll call it pipe 21. Give that a feed stream. And now what I'm going to do is I'm going to fix the pressure drop in the pipe and have it calculate the flow rate instead. So let's see if that works. And what you can see is that pipe 21 is giving me grief. If I come up to the top, you can see straight away the Reynolds number is quite a long way off. You'd expect that. I've got a pressure drop being defined. So I'm going to, it's a relatively large pressure drop, so I'm going to anticipate having a large flow, so my Reynolds number is going to go up a lot. Interestingly though, it's trying to push my Reynolds number negative and it's trying to push my velocity negative. That's a bit troubling. It doesn't let them go negative, so it's going to prevent it taking a full Newton step. And so then at my next iteration, I'm going to again push that velocity and Reynolds number, and now I'm pushing down very negative. And again, that's a bit worrying. I've got stuff stuck on my lower bound. I am improving my solution, but now I've got a singularity, so it's arbitrarily perturbing F inter. That's not great. So if I keep looking at it and keep coming down, it's then run into some sort of trouble, and it's really not converging that DP flow relationship. And again, it's the DP flow relationship because it's labeled DP flow, and I've labeled that with the equation here. The bright among you may have spotted the error already, but it took me a little while to get there. So let me show you what I did to troubleshoot this. What I did was I created this Type 3 version of the model, and what I've done here is I've added another intermediate variable, F turbulent, and then I've given myself this initialization mode, so that if I say initialization mode is true, I'm going to fix my F, and then I'm going to calculate F turbulent, but not use it for anything. And then in the equations for the Darcy-Weisbach system, rather than calculating F, I'm calculating F turbulent. So what it's doing is it's sort of decoupling parts of my problem and allowing me to solve maybe some complex nonlinear equations, but not force the pressure flow relationship to cascade through the rest of my model. This is actually quite a useful cheating technique to get the model to converge the first time, and then once you've got a reasonable initial estimate, you can flip over and forget about the initialization mode. But it's one that I found quite useful and recommend. Okay, so let's do that. Let's get rid of this one that we know doesn't work. Let's drag pipe 3 in. Let's give it a feed stream and hook it up. Let's free the flow rate on that and fix the pressure drop on the pipe. Okay, so we've got that fixed. That's all working well. Let's hit run. And again, it fails to converge. That's irritating, isn't it? Why is that? Well, now we can come back up and we can have a look. And we can see that what's failing to converge is this single nonlinear equation, rather than being a set of 5 equations solving simultaneously. And what it's saying is that DP flow is really, I'm not happy with. My velocity starts off at 1, I'm trying to force that negative. It hits the bound of 0, it's still trying to force it negative. So there's definitely something touchy about that DP flow equation. And what is it? If I come in and look at my pipe, it's me being stupid, of course. What I've done is the DP should be negative if the pressure is dropping. And in this equation, if the DP is negative, if the DP is positive because of this negative sign, everything else in this equation is fixed. So I fixed my my F as initialization mode. So what it's trying to do is to say, well, to get a positive pressure drop, I need to have a negative velocity. That's not feasible, and so I'm giving up because velocity is defined as non-negative. So what I've done, of course, is I've got the wrong sign on my DP, and so really what I want to do is come into the system and have it have a pressure drop of minus 0.01. And if I then do that, then of course it converges nicely and gives me reasonable solutions. I've got an enormous flow rate through the system. Instead of 1,000, I've got 200,000 kilos now, so I've got a relatively big pressure drop with a relatively low resistance. But nonetheless, it's converging and it's working well. So a final thing I would do if I was doing this thoroughly is I would come in and give this a value of minus 0.01 as its default, and I would give an upper bound of 0 to prevent it from to prevent me from being able to put in a foolish number for pressure drop, but also to prevent ACM, if it's calculating the pressure drop, from forcing into an infeasible region. So with those changes in place, my model should now be a lot more reliable. It should converge a whole lot better. Thank you very much for paying attention.